Good afternoon, everyone. I'm Jinzhu, and I'm a PhD student at Tsinghua University in the Inspiring Group. I'm very excited to be here and present our work, Bring on Switch, towards advanced intelligent network data plane via NN-driven traffic analysis at line speed. First, let me introduce the concept of intelligent network data plane. The traditional machine learning-based traffic analysis deploys learning-based models on either end host or network control plane. However, the data movement across the network planes and the batch processing of CPU or GPU becomes the bottlenecks of online traffic analysis, which cause low throughput and high latency. Today, the emerging programmable network hardware enables intelligent network data plane. For example, the protocol-independent switch architecture supports customizable packet processing and stateful storage on programmable switches, making it possible to run machine learning inference on the network data plane. However, to ensure high-speed traffic forwarding, there are significant computation and storage constraints on programmable switch, posing challenges for deploying intelligent models. As prior traffic analysis art targeting intelligent network data plane, neural network on the NIC deploys multi-layer perceptron on the smart NIC by single-bit model representation and bitwise calculations, while NetBeacon deploys decision tree-based model on the programmable switch by ternary matching and efficient range encoding. In the same manner, their models rely on advanced feature engineering to boost accuracy. However, we find fundamental limitations for feature engineering in INDP. First, many critical features are impossible or difficult to directly compute on the data plane, such as the variance, frequency, and percentile of packet lengths. Second, flow statistics could be dynamic as a flow proceeds. Existing solutions need to train independent models for different positions in a flow, and an inference error cannot be corrected until the next inference position. Third, computing and storing these features on the data plane consume a lot of stages and storage. Finally, they need to select flow features carefully to boost accuracy and avoid overfitting in the same time. Therefore, we want to expand the boundaries of INDP to new models that are not limited by the availability of flow features. In Bring on Switch, we introduce recurrent neural network for on-switch analysis, which takes raw packet metadata recurrently and outputs latest inference result for each packet. Moreover, even with careful designs, there is still a significant accuracy degradation from the advanced models like transformer to the limited models on the data plane, especially in difficult traffic analysis tasks. Thus, we want to complement the on-switch RNN with an off-switch transformer-based module to boost the overall accuracy of traffic analysis. The key to co-design with the off-switch module is processing the vast majority of traffic on-switch and only escalating a small portion of ambiguous flows to the off-switch module. We have to address several challenges to realize our motivation. First, it is challenging to realize on-switch RNN inference. For example, RNN executes complex calculations in each time step and records hidden states through consecutive time steps. But on the programmable switch, only simple operations like add and bitwise XNOR are supported, and each register can only be accessed once through the pipeline. Second, to boost the accuracy by analysis escalation, we need to classify the vast majority of traffic on switch and identify the flows with insufficient confidence accurately. Then, we need to construct an efficient system to analyze the escalated flows with a transformer-based module online. To address these challenges, we propose Bring on Switch, a hybrid traffic analysis system. with a co-design of an on-switch RNN, an off-switch integrated model inference system, and a carefully designed flow escalation mechanism. BOSS has three main design goals. First, realize complex RNN computations using a set of data plane native operations. Second, construct an integrated model inference system for fast online traffic analysis with transformer. Third, design an escalation mechanism to accurately identify the flows with insufficient confidence from on-switch analysis. We propose a data plane-friendly RNN architecture to realize on-switch RNN inference. It takes the length and inter-packet delay of each flow packet as input and contains three building blocks: feature embedding, RNN cell, and output layer. To realize the complex computations on the switch, we add a straight-through estimator after each layer to binarize our activations to 1 or -1. Our model weights remain in full precision, which achieves lower accuracy loss than full model binarization. Since all activations are binarized to 1 and -1, the input and output vectors of any layer are essentially bit strings, and we can realize equivalent input-output mapping of a layer by looking up a match action table, regardless of what computations are actually in the layer. To execute consecutive RNN time steps, a straightforward way is to store the hidden states for each flow. When a packet arrives, we read the previous RNN hidden state, perform layer forward propagation, and then update the hidden state. Unfortunately, due to hardware constraints, each register can only be accessed once, and we can't realize these operations in one stage. Thus, we expand RNN steps in serial stages. In particular, we store a sequence of packet embedding vectors for a flow. For each packet, we calculate its embedding vector, update the sequence in storage, and execute all RNN steps for this sequence in serial stages. Since the number of switch stages is limited, expanding RNN time steps into serial stages would also limit the total number of steps executable in our model. To address this problem, we design a novel sliding window mechanism that can recurrently apply RNN inference on fixed-length flow segments. In particular, we store the embedding vectors of the latest S packets in the flow. When a packet arrives, we take these embedding vectors and execute ith RNN steps to obtain an intermediate inference result, which is a vector of probabilities, one for each class. As the flow proceeds, we shift the window by one packet to processing a new segment of embedding vectors repeatedly, which produces many intermediate results. For the latest packet, we accumulate all previous intermediate results and select the class with the largest cumulative probability as the final result. After achieving on-switch RNN inference, we design an analysis escalation mechanism to accurately identify the flows with insufficient confidence from on-switch analysis, and forward these flows for escalated analysis using advanced models. In particular, we measure the confidence of a packet using the largest cumulative class probability divided by the total number of intermediate results. A packet is considered ambiguous if its confidence is below a predefined confidence threshold, and whether a flow should be escalated is determined by the number of ambiguous packets in the flow, using another escalation threshold. The confidence threshold and the escalation threshold are learned based on the confidence distributions in the training samples. An appropriate confidence threshold should escalate as many misclassified packets as possible without affecting correctly classified packets. To this end, we designed two loss functions to train our binary RNN, which enhance the confidence differences between misclassified and correctly classified packets. At last, we build an integrated model inference system that enables fast off-switch inference with a transformer-based model. The system orchestrates 4 types of stateful and single-threaded tasks to realize a non-blocking traffic processing pipeline. We use DPDK in parser thread for fast packet parsing and leverages GPU in analyzer thread to accelerate the inference of transformer. We implement a prototype of BOSS on Barefoot Tofino 1 programmable switch and connect the switch to a server for packet generation and another server for IMS processing. We use packet-level macro accuracy and data plane storage consumptions as the metric and evaluate BOSS on 4 traffic analysis tasks. The baselines are neural network on the NIC and the NetBeacon. For the end-to-end traffic analysis accuracy across 4 tasks, BOSS achieves an average F1 score improvement of 13% and 31% than NetBeacon and the neural network on the NIC, respectively. On more challenging tasks with more classes, the improvement is even greater, up to 17% and 39%. For the hardware resource utilization, BOSS uses around 20% of SRAM in 4 tasks, which is of similar size to NetBeacon. And BOSS uses only around 1% of TCAM in 4 tasks, which is 20 times less than NetBeacon. We also explore the factors affecting the performance of BOSS. For analysis escalation, this figure shows the trade-off between the amount of escalated flows and the improvement in overall accuracy. It shows that BOSS effectively accommodates the off-switch analysis module to compensate for on-switch analysis, and the help of our new losses. In this figure, we tested the system performance of the off-switch IMS. When the number of concurrent flows is below 4096, the maximum end-to-end latency imposed by IMS is less than 2 seconds, even for an inbound rate of 10 million packets per second. The throughput of IMS is sufficient, as we typically escalate only less than 5% of flows to it. In this figure, we perform scaling tests of the entire system. The macro F1 scores of BOSS remain nearly identical as the throughput achieves 100 Gbps, and reveal a sublinear decline as the throughput achieves 1.6 Tbps. As conclusion, BOSS is an online traffic analysis system which is powered by the co-design of an on-switch RNN, an off-switch integrated model inference system, and a carefully designed flow escalation mechanism. As a result, BOSS can process over 95% of flows with the on-switch RNN accurately, and escalate the remaining ambiguous flows to the off-switch IMS, outperforming prior works in accuracy, scalability, and hardware resource utilization. Here are the addresses of our source code and homepage. Thanks for listening. It's time for questions.